Welcome back, students. In this video, we are going to talk about diastereomers. Let's really quick recap some stereoisomers. First of all, we've talked about stereoisomers in general. These are compounds that have the same connectivity, but they differ in how their atoms are pointing in space, so the direction that the atoms are pointing. Then we talked about enantiomers, where enantiomers were compounds that are stereoisomers, so they have the same connectivity, but they are mirror images of one another. So these mirror images were non-superposable. When you put them on top of one another, they did not coincide. And now in this video, we're going to talk about diastereomers. These are compounds that are still stereoisomers. They have the same connectivity, right? So they're not constitutional isomers. So they have the same connectivity of their atoms. They differ in how the atoms are pointing in space, but they are not mirror images of one another. We've actually already looked at a type of diastereomer. These diastereomers that we looked at were cis-trans isomers, and we looked at them in two contexts. The first context was with respect to alkenes. When we looked at an alkene, we found that we had two sp2 hybridized carbons that were making up that double bond. And when we had a group here and a group here that were opposite each other, we called that a trans isomer. Whereas this one we called a cis isomer because the two groups in question were on the same side. These two molecules, they have the same connectivity. They have a CH3 and then a carbon that's sp2 hybridized, and then bound to another carbon that's in a double bond, and then another CH3. So they have the same connectivity, but they're not the same molecule, and you know what? They're not mirror images. So these are types of diastereomers. The other type of diastereomer that we've already seen were still cis-trans isomers, but they were in the context of a ring. So in these two situations, we're looking at the ring as if it's in the plane of the page. And in the first one, we have two methyl groups that are both coming out of the plane of the page. And those two methyl groups are on the same side of the ring with respect to one another. So we would call this cis. Whereas in our other structure, one methyl group is going behind the plane of the page and one is still coming out at you. And these two methyl groups are on opposite sides of the plane of the ring, and because of that, we call this trans. If we look at these two molecules, they have the same connectivity, they have the same chemical formula. Where the methyls are coming off, right, are in the same place. That's the idea of the same connectivity, but they're not mirror images, and they're still not the same compound, because here are the methyls going behind the plane of the page, and here are the methyls coming out of the plane of the page. So these are, again, another type of diastereomer. When we talk about diastereomers and enantiomers, I want to bring your attention to two ideas really quick. If you have one chirality center for a compound, then you're expecting a pair of enantiomers. As soon as you graduate to two chirality centers, then you have the opportunity to have enantiomers as well as diastereomers. So you're actually going to have the potential, I'm going to write potential in there so that we don't freak out on the next slide. And then once we actually draw out those pairs of enantiomers, I'm going to show you what the relationship is with respect to diastereomers. Let's do that on the next page. So on this page, I show you a structure of 1,2-dichloro cyclohexane, but there's no stereochemistry here, right? I'm not showing that the chlorines are pointing a certain direction. What we can do is look at these two carbons and say those two carbons that I put an asterisk next to are both chiral centers. If we have two chiral centers, then the way that we can figure out our total possible number of stereoisomers is with this formula, where n is your number of chiral centers. In this example, where n is 2 because you have 1, 2 chiral centers, you're going to have 2 to the second power, so there's a total of 4 possible stereoisomers. Let's draw those stereoisomers. And we're not going to draw them in any particular order. We're just going to end up drawing all 4. For me personally, I just like to start with both of my substituents wedge. I just feel like that makes me feel consistent. Now we'll go back to that idea of drawing enantiomers that we've done before, right? When we drew the first stereoisomer, and it doesn't matter which one you draw first, it's just my personal preference to draw them both wedge first. We put the mirror behind the plane of the page, and that's going to get us the same connectivity, but a different direction for our wedge and dash bonds. So now we have an enantiomer. Notice how I did enantiomer in quotes, because these are actually the same compound. In our enantiomer video, we looked and saw how that if we had a enantiomer that we drew, we needed to just double check really quick to make sure that our enantiomer that we drew wasn't really the same compound. And so I drew this green line to show that that's where I'm going to rotate, to then take that molecule and mentally place it on the other one and say, hey, when I take those chlorines that are pointing behind the plane of the page and I rotate that 180 degrees, now the chlorines are coming out at me. These are actually the same molecule. So even though I have a total of 4 possible stereoisomers, that's the maximum. If there's an internal plane of symmetry, which is, there is one here, right? If I look at where I drew that green line, the top and the bottom are symmetrical across that green line, that this is really not a stereoisomer that we're going to draw. You would draw one or the other, but not both. Now let's look at how to draw the next set of enantiomers. We've already said that I started with my 2 chlorines being wedge. Now, in order to draw another set, I'm going to start by drawing a diastereomer. In order to draw a diastereomer, you keep the direction of one of the chlorines and you change the other direction. This is really where the heart of the idea on the previous slide came into play. Only when you end up having 2 chiral centers is when you can open the door to diastereomers. I mean, if we're talking about something that's chiral and not, cis-trans isomers with respect to alkenes. But once you're talking about chiral centers leading you to diastereomers, you need to have at least two chiral centers in order for you to have a diastereomer. So these 2 right here, these are diastereomers of each other. Now that I've drawn one chlorine as wedge and one chlorine as dash, I can draw the enantiomer of this by imagining there's a mirror behind that molecule. So I'm going to take that chlorine that's wedge, I'm going to turn it into dash. I'm going to take the chlorine that's dashed and I'm going to turn it into wedge. And these 2 are enantiomers of each other. Hopefully you're also wondering what the relationship is between the first compound and the last one that I drew, and those are also diastereomers. So when you look at a compound, you want to figure out how many chiral centers there are. And then once you figure out the number of chiral centers, you can determine the total number of potential stereoisomers for that, keeping in mind that not every stereoisomer that you draw will actually be a stereoisomer, because like we saw for this first compound, that internal plane of symmetry threw us off. Now there's a name for that kind of compound, and let's talk about it. So I'm going to redraw that first compound where my chlorines were both wedge. This compound has that internal plane of symmetry here where I've drawn. So what does internal plane of symmetry mean? It means where I've drawn that line, this bottom part will mirror the top part, right? So that is an internal mirror plane. When you have that internal mirror plane, this compound has its own name, and it's called a Meso compound. Now notice it's singular, right? A meso compound. So enantiomers come in pairs. Meso compounds come in the singular. So a meso compound, if you draw its so-called enantiomer, you've really just drawn the same compound. You've got to start watching out for those internal planes of symmetry, and you should probably be starting to think, you know what, molecular models might not be a bad idea. Let's do an example. I want you to look at these and state the relationship between the pairs of compounds. So the relationships now that we've graduated to including diastereomers can be things like constitutional isomers, the same compound, enantiomers, or diastereomers. Technically, we could also throw in not isomeric, but in this case, I made them all isomeric. All right, so go ahead, take a moment, and then let's compare answers. For this first compound, this one is a little bit tricky because what we're doing here is we're actually employing two mirrors on this compound to get the second one. So what I see is if I look down this line and I go ahead and I give this a twist, what occurs when I give that a twist 180 degrees is the pi bond ends up being on the right-hand side, and your dashed bond turns into a wedge bond. So these are really the same compound. When you're looking at these, one of the things that I noticed right away was I changed the direction of wedge to dash and also changed the location of the pi bond. So I did a double mirror. I had a mirror both behind my compound and to the right of my compound. And when you mirror it twice, you just get the same compound. So these are the same compound. Let's look at the next one. If we look at the next one, this is a pair of enantiomers. You see that you go from wedge to dashed and dashed to wedge. So that makes these enantiomers. If you wanted to double check to make sure that these were non-superposable, what you would do is take one of the compounds, draw a line through the middle, and mentally rotate along that line. When you do that, you see that now your CH3 would be up here, and that does not correlate with where the bromine is. The third one on the bottom left might have tricked you. That is not a chiral center. These are the same compounds. There you go. I put that question on my final literally every single year because it's so easy when you start doing these to look at this and just see wedge and go, oh, that's got to be a chiral center. No, it doesn't. It doesn't have to be a chiral center. It can just be us drawing something in 3D, because if we draw something flat, we're not actually illustrating what the compound looks like in real life. We put in those wedge and dash bonds not just to communicate chiral centers, but to communicate that this is a 109.5 degree bond angle. So really watch out and first assess, is this a chiral center? And then go on and utilize the rest of your knowledge. This final one, this is a pair of diastereomers. These are diastereomers because I started with wedge, I ended with wedge. Right, so one chiral center didn't change, but my other chiral center did change. And that's what makes these diastereomers, because they have the same connectivity, but they are not mirror images of each other, and they are not the same compound. Let's wrap up. In this video, we did a quick review of stereoisomers, and then we dove into diastereomers. We'd actually already seen diastereomers before. We just needed to remember that what we had seen are technically diastereomers. Then we defined a meso compound and practiced defining the relationship between pairs of compounds, which you should absolutely be prepared to do on a test. As always, thanks for your attention. This is Katoni signing out.